This is Chapter 4, Unit 4. We're talking about sample variability. Sample variability. We're still talking about how variable scores can be when you put them together in a distribution. So look at the diagram on the right. The population is shown as a normal curve, and notice how far the tail goes on the left and the right. There's a lot of outliers in this population. But now let's talk about what happens when we choose a sample out of the population. When you choose a sample, you don't always get those outliers that are in the population. So the variance of a sample tends to be much smaller because the range of scores is smaller. So a sample statistic is said to be biased if it overestimates or underestimates the corresponding population parameter. So anytime a sample is chosen out of a population, it's very unlikely that it's going to have the extremes on either side of the distribution that the population had. And again, the sample scores won't be as spread out, so this makes variability less for a sample. Thus, the sample variability gives a biased estimate of the population variability. But we can easily apply a correction for sample variability to make it look more like the population variability and stretch it out. So the sum of squared deviations, SS, as we did in the last unit for a population, we're going to do the same exact formula for a sample. And it looks exactly the same, except instead of a Greek letter mu for the mean, we have a capital N for a sample mean. And the computational formula also looks exactly the same, except instead of having a capital N for a population, now we have a small n for a sample. So these formulas for sum of squares are always the same for population or a sample. They are never different. Let's talk about the sample formulas. Again, sum of squares for a sample is exactly the same formula as a population, except with a capital M for mean and a little n for the number of scores. So variance here is a little bit different. Notice the formula for variance is S squared. That doesn't mean we square anything or do anything different. S squared is the notation that we give for variance. And it's equal to SS over N minus 1. Whereas in a population, it was just SS over N. Remember that sample variance needs a correction to make it a little bit wider so it mimics the population variance. So the way we do this and the way we correct is use N minus 1. And then the standard deviation for a sample is just S is equal to the square root of SS over N minus 1, or the square root of S squared, the variance. Let's look at an example, finding sample variance and standard deviation. So I'm giving you some scores here. The first step you're always going to do is you're going to make an X column and an X squared column. You're going to square all the scores for the X squared column, and then you're going to sum up both columns, because you always need a summation of X and you need a summation of X squared. Okay, and a lot of times you need the mean. So once I have the columns made, I usually calculate a mean, which would be summation of X over N, which gives me 6.5 for this problem. The second step, I'm going to compute the sum of squares using the sum of squares equation. So again, it's the big number, which is 386 in this case, minus the small number, which is 52, squared over N. So fill in all the numbers, do the math. Remember to do the right side of the equation first and simplify that fraction, and then subtract at the very end to give you 48 for sum of squares. Next step is finding the variance. Well, the variance formula just says variance equals SS over N minus 1. So you put in 48. N minus 1 would be 8 minus 1, which would be 7. You get 6.86. And then finally, the standard deviation is just the square root of the variance. It gives you 2.62. Okay, let's keep going with that example that we had a minute ago. Let's look at what a histogram would look like. So in order to make a histogram, with some different items we're going to talk about to put on it, first you find the mean, which we found in the last example of 6.5. Then we're going to find the range of scores. So let's look and see which scores are furthest from 6.5. Well, the smallest score in that data set was a 3. So the difference between the mean and that score is 3.5 points. The largest score in that data set is 11. So the distance between that score of 11 and the mean of 6.5 is 4.5 points. So the largest score, the largest range, is 4.5 points away. Okay, and I can estimate the standard deviation by dividing that range by 2. So that would give me an estimated standard deviation of 2.25. Okay, and if I was going to draw it, it would look like this. There's my histogram. There's all my scores. I would put a line where the mean is. The mean was 6.5. And then I would say which score's closest to the mean of 6.5. Well, you could choose 6 or 7. Either one is a half a point away. Okay, so we chose 6 here. And then the furthest point away is 11. So between the mean and the furthest point is 4.5 points. So we label that on there. And then again, remember that the furthest point is typically 2 standard deviations away from the mean. So to find 1 standard deviation, we just divide that furthest point away in half. And that's how we got an estimated standard deviation of 2.25. All right, here's another example. So here's 5 scores I've given you. Same exact procedure, make an X column, add them up, make an X squared column, add them up, find the mean, which would just be 20 divided by n, which is 5, so 20 divided by 5 is 4 is the mean. Step 2, compute the sum of squares, biggest number minus the smallest number squared over n. Fill in all the numbers you need. You should get 36. Find the variance, which is just s squared equals ss over n minus 1. N is 5, so n minus 1 would be 4. So I end up with 9. Standard deviation is just square root of the variance, so I end up with 3. So let's talk about the estimation of population variability. Again, sample variance is often called estimated population variance. Sample standard deviation is often called estimated population standard deviation because we're picking samples in order to estimate what the population looks like. So when you only have a sample to work with, the variance and the standard deviation for that sample provide the best possible estimates of the population variability. All right, let's talk about degrees of freedom for sample variance. Suppose you have a sample with 3 scores that has a mean of 5. Well, you're given 2 scores. These scores, and you're told that can be any number. However, the third score is going to be restricted because it has to have a certain value so that the mean of all 3 scores is equal to 5. So here's an example of that. Say you have a mean of 5 and you're going to choose scores 2 and 9. Well, you can't choose the third score. The third score has to be a score of 4 because if you took the mean of 2, 4, and 9, that would equal 5. So can you see how you can't choose that third score? It's not free to vary. You don't have the freedom to vary that third score. Okay? So because that last score is always restricted in statistics, the degrees of freedom is df equals n minus 1. So for 3 scores, only n minus 1 scores can vary, and 3 minus 1 is 2, so that gives 2 scores that can vary. The last score is always restricted. Here's an example of degrees of freedom. So say you have 7 hats, and you want to wear a different hat each day of the week. Well, for 6 days, you have a choice from the remaining hats in your closet. But when you get to that last day, there's no choice. There's only 1 hat left. You have to wear what's left. So that's kind of what we're talking about when we say n minus 1. So the degrees of freedom that you have is n minus 1, and it's abbreviated by df. So if we look again at the sample formulas, sum of squares are the same. Variance, though, can also be written not only as ss over n minus 1, but you could write it as ss over df because df is equal to n minus 1. So a lot of times you'll see formulas written this way. And the same thing for standard deviation. Instead of n minus 1, df would go into the equation. They mean exactly the same thing. Okay, so here's a learning check. See if you can work the problem and pause the video. All right, which of the following explains why it's necessary to make a correction to the formula for sample variance? Okay, the answer would be A. If the sample variance would be computed by dividing n instead of n minus 1, then the values would underestimate the population variance. We have to divide sample by n minus 1 in order to make the sample variance a little bit larger so that it matches population variance. All right, pause the video for problem 2. See if you can do it. All right, problem 2. Under what circumstances is the definitional formula preferred over the computational formula when computing SS, the sum of squared deviations for a sample? The answer would be A. When the sample mean is a whole number, then it's really easy to use the definitional formula. And a lot of statisticians like me, though, just find it easier to use the computational formula all the time. Then you don't have to worry about when to use one or the other. All right, last learning check, problem 3. Here's some scores. I want you to find the variance and standard deviation. Pause the video. All right, step 1, you're going to make an X and an X squared column. Compute the values. I found a summation of X equal to 15. I found a summation of X squared equal to 81. And I went ahead and computed a mean. I found a mean of 15 divided by 5, which gave me 3. For step 2, compute the sum of squares. Again, the big number, 81, minus the small number, 15 squared, over n, which is 5. And remember, sum of squares, you do not use n minus 1. It's the biggest mistake people make on this test and quiz when they're talking about samples. You only use n for sum of squares. Okay, solve for sum of squares, you get 36. Then here's the variance. This is where you use n minus 1, only talking about variability. Plug in your numbers. 36 over n minus 1 would be 5 minus 1, which is 4. And that gives you a variance of 9. For standard deviation, just take the square root, you get 3.